Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. So I'd like to start off our event today by thanking CrowdFlower for sponsoring today's event. CrowdFlower is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide very useful information into a wide variety of topics of interest to our data science community. Now, today's webinar is entitled Practical Human-in-the-Loop Machine Learning by CrowdFlower. But before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have one presenter who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation because we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Robert Monroe, with CrowdFlower. Now, Robert is Chief Technology Officer at CrowdFlower. He's an expert in combining human and machine intelligence, working with machine learning approaches to text, speech, image, and video processing. Robert has founded several AI companies, building some of the top teams in artificial intelligence. He's worked in many diverse environments, from Sierra Leone, Haiti, and Amazon, to London, Sydney, and Silicon Valley, in organizations ranging from startups to the United Nations. Now, he most recently ran product for Amazon Web Services' first natural language processing services in the deep learning team at Amazon AI. Robert's published more than 50 papers and is a regular speaker about technology in an increasingly connected world. He has a PhD from Stanford University. So, Robert, thanks for being with us. We're looking forward to your presentation. So, curious about what human-in-the-loop machine learning actually looks like? So join CrowdFlower and learn how effectively to incorporate active learning, transfer learning, and annotation quality in your machine learning projects to achieve better results. So in today's Data Science Central webinar, we'll cover when to use human-in-the-loop as an effective strategy for machine learning projects, how to set up an effective interface to get the most out of human intelligence, how to ensure high-quality, accurate training data sets, and how to use machine learning models from different domains to improve your own labeling. So in today's webinar, we'll include an end-to-end look at setting up and running a job that generates high-quality training data and shows how to incorporate that training data into human-in-the-loop machine learning systems that you can run in your own environment. So Robert, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill. It's a pleasure to be here today at Data Science Central and to chat with everyone who has joined us to learn more about active learning and transfer learning. Before we jump into the talk itself, we'd love to get an idea of who exactly is joining us today and what their background is. So if you could fill out just 2 poll questions that we'll put up, we'd really appreciate that. The first one is this one here. What is your primary job role? So if you could please respond whether you're a data scientist, you work in other parts of IT, you work in a line of business, maybe in sales or business development, or you're joining us as a researcher or a student, or maybe just a student of life here today, then please let us know. And we'll give you just a few moments there to fill out that. Okay, I hope you had the chance to fill out that first poll question. Let's have a look at what the responses were there. Wow, okay, we've got a mix of people. So about 40% work in data science. So that's great to see. I'd imagine that most of you do have a background in machine learning already, but perhaps not active learning or transfer learning. And it looks like another 20% of you are technical, with about 15 coming from non-technical line of businesses. So I think that there should be something for everybody today. And probably a good point to point out that we'll also be sharing some starter code for this. So those of you who are technical can take advantage of that after the webinar finishes. Our second and final poll question, how advanced are your organization's machine learning efforts? So if you are in an organization that uses machine learning, is it something that your company is already using extensively? Is it something that you're just getting started on? Is it something that you're planning or evaluating? Or if you're just here to educate yourself on this topic, please let us know that too. All right, so thank you everyone for your responses there. And all right, 40% of you are already using machine learning extensively, or almost 40%. That's a great result. So really hoping that we'll be able to extend your expertise here today. I also love that 30% of you are just here to educate yourselves. This particular part of machine learning, the interface between humans and artificial intelligence, is, I think, the most exciting, but one of the least researched areas of AI. So I'm glad that you're here to learn more about that. So like Bill said, I'm the CTO of CrowdFlower. My PhD was in natural language processing at Stanford University, although I worked extensively in image recognition, and in fact, all the examples today will draw from image recognition, but will equally apply to machine learning, whether it's applied to images, to videos, to audio, to text, to time series data, or to any other kind of signals that you are trying to process. So the goals for today is to help you get started in thinking about how to effectively incorporate active learning, transfer learning, annotation quality into your machine learning projects. So at the end of the talk, you should be able to answer the questions. When should I use human in the loop for machine learning projects? How can I set up an effective interface to get the most out of human intelligence? How can I ensure high quality, accurate training data sets? And how can I use machine learning models from different domains to improve my labeling? So a lot of this falls within what's known in the academic community as active learning. And so the three main areas from an academic standpoint that we'll be discussing today are active learning, transfer learning, and data annotation. So I'll talk about what active learning is, why it's important, but also why it's overlooked. So at a really high level, active learning is the process of selecting the optimal data to manually label for machine learning. And this is often a continuous feedback loop. So let's imagine that you have a simple image classifier and you want to train it to identify pictures of cats. So you're given your machine learning algorithm, your little robot, some number of pictures of cats, probably more than one, probably thousands, and you're asking it to make predictions about whether something is a cat or not. The active learning is the bottom loop here. It's the machine learning algorithm or a set of supporting algorithms trying to decide which are the optimal unlabeled images for which you want a human to verify whether or not they're a cat. And so you can see in this example here, there's a kitten and there's a tiger. So you can imagine that these are not prototypical cats. These might have been things that the machine learning algorithm was confused about or simply hasn't seen before. And so they're likely items for review. And this is the high-level intuition that goes behind active learning. So what's potentially confusing for the machine learning algorithm? What hasn't it seen before? How can we look across a large number of unlabeled examples to find out what is the right ones for human review? And the reason that this is important is because we are often applying machine learning across millions and millions of data points, and it is not either in terms of the economics or the simple time feasible to provide a human label for every single one of those data points. And so you know that you can do better than simply randomly selecting items for human labels, but it's not always clear what that strategy should be. And so active learning would be this process here of these many, many different pictures of cats. Let's say these 5 are the right of this subset for a human to take time to review. Active learning in industry is often overlooked because of what's essentially an inherent bias within the academic community. So historically, most AI research, especially in supervised machine learning, has kept the data constant and looked at different algorithms. So if you go to any AI conference, whether it's in computer vision or in natural language processing or in other subfields of machine learning, you'll see that probably 90% of the papers are evaluating different kinds of supervised machine learning algorithms over the same data sets. However, in industry, you'll often find that you can get just as much increase in accuracy and many times greater increases in accuracy by adding more training data. And so I've certainly seen cases where entire PhDs have been spent getting, say a 5% increase in accuracy over a difficult task, where that 5 cents could also be found from just 10 minutes of additional human labeling of training data. I don't think this is very controversial in industry. I think most people who have worked in practical machine learning have found this, but because this just simply hasn't been much of the science historically, it's often overlooked. So we're really happy to be able to plug some of that gap with webinars like this one. And here are just some simple stats. So if you look at papers in ACM over, I forget this time period, I think it might have been the last decade, you'll see that mentions of machine learning, artificial intelligence are in the tens of thousands, and active learning is only mentioned about 1,000 times. So order of magnitude, less focus relative just to changing the algorithms themselves. So transfer learning is even less well studied than active learning, but it's seen a huge resurgence recently. So transfer learning is using the data or model from one problem to help solve another problem. It's important because it can increase the accuracy of your model with less training data. So in the same way that active learning can reduce the number of human labels that you will need in your training data to reach a certain level of accuracy, you can also take advantage of an existing pre-trained model or data from another problem, which might be able to be easily adapted. It's not that widely used in industry, or at least it hasn't been historically, but it's just starting to get widespread use, especially in computer vision. So if those of you might have seen that Google Cloud released a product called AutoML really, I think it's in the last couple of months. It might have been this year. And it uses transfer learning. So it's a system that allows you to do image classification according to your own set of labels, but you get a running start because that model isn't starting from scratch. It's using transfer learning behind the scenes from a very large collection of millions of images that Google already has labels for. What's interesting here is that we're seeing these huge leaps and bounds in transfer learning in computer vision, but not yet in natural language processing. So certainly here at CrowdFlower, we've successfully seen transfer learning between computer vision data sets of everyday objects to things which seem really different, like medical imaging or satellite imagery. So fairly successful use of transfer learning across domains. However, when you look at something in language which seems very closely related, let's say sentiment analysis on Twitter posts versus sentiment analysis on Yelp reviews in the same language, you only see like a couple of % increase in accuracy. So hopefully there'll be more advances in transfer learning so that we can take greater advantage of it in language tasks. But certainly at the moment, the biggest leaps and bounds in the industry have been in computer vision. So there's 2 different ways that transfer learning is applied. The first is the kind of historically most widely used. So you're using the output from one classifier as the input into another. So here, imagine that this is a image recognition task, and these different boxes represent different layers in your model. So you have raw pixels going into the first layer in your model. Subsequent layers are abstracting over those pixels to find textures and edges, and you can see in that final image there individual objects. So things that look like pumpkins on the bottom left, or heads and torsos in the bottom middle. And the classic way that you could use transfer learning and works with any classifier is you can use the output from one into another. So let's say that you had a classifier that already classified things like everyday objects like cars, trees, houses, etc., in their existence in images. So that means that you could then have a classification algorithm that took in raw pixels from each of the images and also took in the output from that classifier. So maybe the actual predictions, or the probabilities, or some score associated with each of the previous classes. And in fact, it could be multiple classifiers as well. And so historically, you'd see this especially when you're trying to chain algorithms together. So for example, in language, using the output of a part of speech or a syntactic classifier as input into something doing more sophisticated semantic analysis. So that's the first kind of transfer learning, really just enriching the feature space of your machine learning algorithm with another. In recent years, and in particular with neural network models, with deep learning models, there's been a lot of success in looking at retraining just the last layer, or maybe the last few layers of a deep learning model. So imagine same use case. So you have a large data set, and in this case it's the Imagenet data set, which we'll be using as an example throughout today's webinar. And you've trained that for the 1,000 canonical classes for Imagenet. But you want to extend that. You want to maybe train for 1,500 labels, or different labels entirely. You can see a lot of success in taking just that last layer and retraining it for the labels that you care about. So rather than the 1,000 labels that come with Imagenet, the say 50 labels, somewhat related but maybe not completely overlapping, that you care about in your data. And what's nice in this situation is that you might only have a few thousand training examples in the data that you care about, but you're taking full advantage of the millions of training examples for which things like the edges and textures have been found for Imagenet, being able to use them as features. And this is the approach that we'll talk about today, and is also in the starter code that we'll be sharing, which is open sourced and you can play around with. Okay, so annotation. So the most important thing in making sure you have good training data is making sure that it really is good training data. So if you're not careful about the ways in which you're making clear instructions, ensuring that people understand your task, and other kinds of quality control that I'll go into, then you're going to end up with training data which will give you essentially a maximum accuracy that you could hope to achieve. So if the data you're training on isn't more than 90% accurate, or doesn't have more than 90% agreement among the people who created that training data, then that puts a rough ceiling on the accuracy that you can expect for your machine learning models. It's pretty rare that you'll get more accuracy from a machine learning model than you will from the quality of that data to begin with. And so where does training data come from? So I love this comic from XKCD. So if you've signed into a website recently, you might see some of the CAPTCHAs are now asking you to identify objects in images. I don't think anyone's actually doing this in real time. No one's going to crash their car. And certainly there's a lot more quality control going on in terms of how this is actually fed into self-driving car algorithms. But there is a little bit of truth here as well. So certainly we'll often see many, many more hours go into creating the right training data than into playing around with the resulting algorithms. So there are a number of methods for ensuring quality training data. I'll give a brief demo of some of these as well. I'll give an overview first. So one of the most important things is in ensuring the correct workforce. So within the CrowdFlower platform, you have access to a number of different workforces. So open crowd, where we have hundreds of thousands of people coming onto a marketplace that we manage. Trusted, so this is people who have worked on our platform often for many years, and we have a historical record of their accuracy. What we call an NDA crowd, so these are groups of people whose identities are known. They're sitting together in work centers all around the world. They can sign NDAs. They can be trained directly for more complex tasks, or also in-house. So it's the fastest growing use case for us in CrowdFlower is people simply licensing our software and bringing their own workforce to provide those annotations. And so the trade-offs here are scalability versus reliability. So the people that you have in-house are hopefully going to be subject matter experts on what you're trying to build models for, but it's a much less scalable workforce than you can get by going to the hundreds of thousands of people in the open crowd or anything in between. And so with CrowdFlower, we have what we call channels, the different kinds of workforces you can gauge, so the different contributors, we call them. And you can dive down into analytics and even see which of those hundreds of groups of people are the most accurate for your task. The second example of quality, and what we find to be the most important, is to embed test questions and gold answers to track quality. So by creating questions for which you already know the answer, you can run a quiz at the start of training, and you can also embed answers throughout someone's work for which you already know the answer, so that you have a good idea of their accuracy, and take action appropriately. So remove them from your task if they're below a certain level of accuracy, or in the test question phase, or programmatically show them what the right answer was, so that they can train and become better at your particular task. The third and most important way to ensure quality, second most important, through embedding test questions, is to give multiple people one task and calculate agreement. Simple Bayesian probabilities comes into play here. So let's say that your workers are all about 90% accurate on your task, and you want your data to be more than 90% accurate in its labeling. Assuming that 90% accuracy really is randomly distributed, if you have two people agree on the label for a task, and you know they are both individually 90% accurate, then collectively that you can be 99% confident on that label. And so by giving the same task to multiple people and looking for levels of agreement, you can get to a very high level of confidence where your data is labeled much more accurately than the accuracy of any one individual. And in the CrowdFlower platform, this is also something that can be run dynamically. So it's something that you can say, I want a minimum of 3 workers, and keep adding more workers, and then finding higher levels until you reach a level of agreement. And so how many people create training data? For us alone, there are hundreds of thousands of people annotating data every day for our customers to train machine learning models. And one of the largest growing groups of these are dedicated business process outsourcers that specialize in creating training data. So here are Imagenet workers, one of the 100 channels that you can access through the CrowdFlower platform, where dedicated groups of workers are paid a guaranteed salary. They have in-house training for whatever the tasks happen to be. In this particular case, is a group of people working on self-driving cars. In terms of what training data looks like, it looks like the output that you expect from your machine learning model. So this is an example of what's called semantic segmentation or pixel labeling. So this is from a self-driving car company that we're working with, and they are labeling, as it sounds like, every single pixel in the image with each color corresponding to a category. So here, blue would be cars, green would be trees, and it looks like that the road is a dark purple. And so this is with the goal of feeding this to a self-driving car so that it can become more accurate in understanding its environment. So in summary, ensuring quality annotations, you want to embed gold known answers to quiz the workers initially and to track accuracy as they continue on. You want to select the right annotators for the job, so whether that's meaning your in-house experts, general crowdsourced workers with the right quality control, or people who have been trained for your specific task. You want to give the same job to multiple people and track agreement. And then there's 3 other strategies which have been well attested for showing increased throughput and accuracy. So breaking up complex tasks into simpler ones. So for semantic segmentation, you might have one task breaking up that image into the different objects and another one labeling them. You want to be smart about removing ordering effects, often known as priming. So for example, if someone's looking at the same category 20 times in a row, they might be primed to mislabel something in that category on the 21st attempt. And then if you have a somewhat subjective task or a task where you think a worker might be biased towards the answer they think that you want, Bayesian truth serum, which is one of my favorite segments in annotation, is a strategy there. So Bayesian truth serum, I'd encourage you to read more about this. The basic idea is you're not asking somebody what they think, you're asking somebody to put what most people would think. So a good example is something like sentiment analysis. So if you're asking people to label whether sentiment around a product was positive, negative, or neutral, you couldn't be creating a bias in that this person might think it's your product, and they don't want to tell you that something negative has been said. And so a lot of really interesting studies have shown that if you ask someone, what would most people say the sentiment is in this tweet, rather than what do you think the sentiment is, then you get much more consistent results. And cross-culturally, that's important for giving people permission to report something subjectively, which otherwise, for reasons of deference or politeness, they might not give the answer that you're looking for. Okay, so with that, we're going to jump into a quick demo of what some of this looks like in the CrowdFlower platform. So I have a really simple task where I just want to classify a number of images, and this will be the same images that you can access in the open source code and data set associated with this webinar, and for which we'll draw the remaining examples. So these are a set of URLs for which we want to classify what kind of sports are present in the images. So this is CrowdFlower platform. I've uploaded a few 100,000 examples here. And then I want to design a task that will allow the contributors who are labeling these images to say what sport is in these images. So here's just the Java design. You can see this looks like a fairly straightforward form. So in the instructions, you're asking people to look at an image, fill out which of these categories of sports are present in it. And this can be defined either in a GUI interface or via HTML. There won't be an example here, but in CrowdFlower we also allow custom JavaScript and CSS for our power users. And so the most important thing to set up is the test questions or the quiz questions. So here's an example here. So for this image, this is going to become a quiz question for our workforce, asking, are there any sports in this image? And we want them to answer yes. And maybe it was ambiguous, so we might have permitted both yes and unclear, but in this case, I think we can permit yes. The person should absolutely click yes. And again, it's not ambiguous between these different sports. So they should select motor racing for this particular example. If it's in the quiz mode and we're giving them the reason why they got this wrong, there's not much to say. This really is car racing. There's no ambiguity here. But this is the message that will pop up to that person who's trying to work on this particular task. So we typically look to set up enough quiz questions so that 1 in 10 tasks that someone is undertaking is actually a hidden gold task. That's what we aim for at CrowdFlower. So what this means is that we want to create enough of these questions so that we have, let's say, 10 in a quiz mode up front to let people into the task and to practice on it, and then 1 for every 10 additional tasks that we want someone to undertake. And so the trade-off here is that if you create more quiz questions, then each individual can undertake many more tasks themselves. Whereas if you create fewer test questions, that's quicker for you, but then you are going to get you're going to have to get a larger number of people in order to get through that entire volume. And then in this case, I'm selecting level 2 contributors. So this is now moving on to thinking about what workforce I want to take part in this. So unleveled is open crowd. Level 1, 2, and 3 refers to how long people have worked on the CrowdFlower platform and what their level of accuracy has been consistently in the past. I'm allowing people internally to use it, although I'm not going to do that here. I'm not sending that out to the NDA channels, to the dedicated workforces. This is an image classification task, so I don't really need to make any other changes, but I could whitelist or blacklist by countries. It's a language task by languages as well. And then I'm not going to do it here, but I could really go into custom channels. So this is a predefined set of workers that have worked on tasks for me in the past. In the advanced settings, I could go in and say which of those hundreds of channels that we partner with could undertake this task. I'll leave that without doing that for now. And then the last step is then deciding on things like how much to run. So to begin with, we run a test run, get feedback, and look to refine the task, improve questions, identify errors. It's something I recommend anyone does, either on our platform or if you're running your own internal labeling. Thinking about the fair amount of payment per individual judgment. And then this is 3 different people working on the same task. And then within the CrowdFlower platform, that's it. So hitting launch then sends this out to the various channel partners where the different contributors can take advantage of the work available to them and start working on this task. So this is something that you want to play around with yourselves. You can sign up tomorrow for a trial account at CrowdFlower. If you are I think it was 30% of people who are researchers or students, we also offer a Data for Everyone program where we waive all the fees for using our platform. You're paying the workforce, or if that's your internal workforce, you're not paying anything, on the provision that you open source your data. So that if you're contributing to the research community and willing to open source the annotations you get from CrowdFlower, we waive the fee for using our platform. So moving on to the active learning component, once you have annotated data, so let's say you initially annotate some subset of your data set, and then you want to start thinking about, okay, now that I have some annotated data, or I have my first model, how do I then approach active learning to decide what's the next data to annotate? So there'll be a link at this webinar as well that you can access later, or you're welcome to search for this now. So this active learning class is open source data for getting started with the examples that we have here, where there's a 4 GB set of sports images. The same ones you just saw us launch the annotation job for, and starter code for getting predictions. And this actually uses transfer learning. So this is a model trained on Imagenet for which you're using transfer learning for your active learning. So this is deep active transfer learning. And if you can say you're working on deep active transfer learning, then you're right at the cutting edge of artificial intelligence research. So with that, I'll go back to some of those examples. So like I said, this example was using Imagenet, and it's building on the well-known TensorFlow library, which I'm sure you've heard of. So Imagenet, the canonical set is millions of images labeled with a little more than 1,000 categories. The categories are from the WordNet hierarchy of tones. So here in this example, you can see that within court games, there are tennis, badminton, volleyball, etc. Most data sets that you'll come across won't be hierarchically labeled. It'll be a flat label. And in fact, most people treat Imagenet as a flat system of labels. So 1,000 plus categories without really taking into account the relationship between those categories. However, in this context, there'll be one advanced example at the end where that hierarchy is important. So for this, like the example we saw earlier, we use a pre-trained deep learning model for Imagenet. It's an inception model for those of you who want to dive deep into the exact architecture. And so same intuition. So this deep learning model are networks of layers where each layer is a further refinement from raw pixels to the target label. And so here's an example output, and this should be familiar to any of you who have worked in machine learning before. So given this algorithm this picture that it hasn't seen before of a person in the canoe, it is predicting with 90% confidence that the correct label for this image is canoe. So I'll just nothing with Imagenet. It treats the images as the categories as mutually exclusive. There's just one label per image. Obviously, your task might be set up differently, but the same intuitions apply. And you can see that the rest of the predictions here aren't terrible either, right? So the paddle is about 5% confidence, gondola less than 1. I didn't see a sandbar here or a snorkel, but you could imagine that they might appear in this context. This looks like a fairly good prediction. And so active learning is the process of looking at these kinds of outputs and the distribution of data and deciding what should humans review to add more labels to. So the most important thing to look for are ambiguous items. So here's another example. If we give this image to the classifier, it predicts with 36% confidence, about 37, that it's volleyball, and 32 that it's balance beam. And these aren't terrible predictions, but they're clearly wrong. This isn't volleyball or balance beam. If anyone in this webinar knows the name of this sport, I'll be really impressed. Feel free to add that into the question space. Just a hint, it's neither basketball nor netball. It's another sport that's like that. So well, these predictions, you can see why they might have made the errors. This looks like it could be a volleyball court. That beam or the railing in front could be mistaken for a balance beam. It's obviously wrong. And so the fact that the classifier has almost equal probability of these two mutually exclusive categories is good evidence that it's not accurate in this case. And so you often see this in the literature referred to as uncertainty sampling. So you're looking for something near the decision boundary between two classes. Another equally important sampling method is to look for low confidence items. And so this is something which isn't known about in your training data. So again, when we put this image into our classifier, it predicts a parachute as the most likely category, but with only 11% confidence. And nothing has high confidence here. And there's no parachutes here. It's not terrible. You know, it's the sky, so you can see what might have guessed parachute. because that's where it's seen parachutes in the past. A geyser or geyser, it's harder to predict why. Maybe this looks like it's water reflecting and therefore a geyser. But the fact that this has really low confidence, this is telling us that this is an item which is unknown to our classifier to date. And so this can be evidence that's something that you want to get a human label on to expand the diversity of what you're looking at. And so this is something you'll see referred to in the literature as diversity sampling. Looking for low confidence in your model is one really effective way to do diversity sampling, but there's others as well. You can look for statistical differences in unsupervised methods between your training data and unlabeled items. You can also look at, depending on your model, other parameters that your model is outputting. One really important thing to remember when you are doing active learning is that you should always evaluate on a random set of items. So you can imagine that if you're continually sampling from hard to classify images at the decision boundary, the accuracy of your model on those same kind of items is going to go down because you're evaluating not on a random set of images, you're evaluating on some of the hardest ones to classify. And certainly you want to oversample hard ones to classify in your training data or make your model more accurate. But if you're not evaluating your model on randomly selected items, you're not actually going to have a way to evaluate whether your accuracy is actually improving, because you're essentially changing what you're evaluating on. So this is the thing that I've seen people get wrong the most. I've done this wrong many times, just forgetting to set aside that additional test set that remains from randomly selected items. In addition, you always want some set of randomly selected items in what you're sampling for human review. This is important because the most valuable items to label are the ones which are confidently wrong. And you want the opportunity to get those randomly selected items. So you can see that if we select this image here and get a classification, it's saying volleyball with 80% confidence. And this is incorrect. It's actually rugby, so a rugby ball would be the correct answer. But if we look at the differences here, 80% versus 3%, we wouldn't have selected this image either by looking for diversity or uncertainty. So the most confident item, volleyball, is really confident. And we can see why. It's on the sand. People are diving. They could be wearing volleyball-like clothing. And then the difference between the 80 and the 3% of the correct one is really, really high. It's worth noting at this point that in academic publications for Imagenet, typically accuracy has been whether any of the top 5 most confident predictions are present. So in academic papers on Imagenet, this would be selected as the correct response. But obviously, there's not many practical applications where this would be kind of an acceptable response. And so some more advanced techniques. You can look at methods either outside of your model, so you can think about clustering. And what's interesting I found is that even basic clustering, like k-means, can be fairly effective. So you can take your unlabeled data set, let's say put this into 100 different clusters, and then you sample from each of those clusters. This is a really good strategy if your data is incredibly biased. So you have a large number of items. Let's say it's during the World Series of Baseball, so 90% of your images are about baseball. Ideally, even unsupervised clustering would put those baseball images together, and that's just one of your 100 clusters. So it's a good way to get a larger diversity of images. I've experimented with some fairly interesting methods with the second to last layer in deep learning models as well. So if you remember back to that image, the second to last layer is when you have something approximating real world objects. And this is a better method for features for clustering than just raw pixels. In text, you can do things like clustering on the words and the phrases. I think that's the right intuition for thinking about clustering on the second to last layer for something like images. Because obviously pixels are often too much of an abstraction to cluster over, but being able to pull out those kind of features in the second to last layer seems to be a fairly effective method for images. In other advanced techniques, if you remember at the start, we talked about WordNet being hierarchical classification. And so you'll often find that there's external resources that you can use, which will tell you when something is ambiguous. So if we apply the classification to this particular image here, we'll see that it's pretty to be a lawnmower or a crash helmet. It's neither of these. It's a motorcycle. And we can see why it might have made these predictions. I guess that could be shaped like a very expensive lawnmower, and maybe the motorcycle spies it towards crash helmet. But if we looked at the WordNet hierarchy, we would see that lawnmower and crash helmet are really distant from each other. So I think it would be okay if it was a crash helmet and a bicycle helmet, which were confused with each other. That would make sense. These are two objects that should look like each other. But lawnmower and crash helmet are really distant cousins in the WordNet hierarchy. So this is something that can give us evidence that the model is not very accurate here. Again, this is an interesting example in an Imagenet. That's actually drawn from WordNet, and there tend to be a large number of existing open source frameworks for looking at distance in text, and there are images, but this is a great one for this particular use case with Imagenet. And finally, you also want to consider to what extent you're oversampling for areas for which there's just inherent ambiguity. So just imagine that most of the confusion in your model came from not knowing whether it was racquetball or squash. So I'm not sure how many of you looking at this image can know whether that's squash or racquetball. I know because I play, but I would forgive a machine learning algorithm for not understanding this. And so if you were only sampling the most ambiguous items, if you weren't careful about the diversity, you'd want to really look at whether or not there are just some inherently ambiguous items in your data set, and to what extent you might be oversampling those. And there are some additional exceptions that you might want to think about. So in a real-world situation, you might care about some labels more than others. And so active learning can be a good way that if it's the playoffs for basketball coming up and you want your model to be more accurate for basketball, that you'll oversample the labels that you care about. But again, making sure you're employing a variety of active learning techniques to ensure you still have diversity and you're being careful about non-user bias into your model, as well as the examples I showed of using clustering or external resources. And like I already mentioned, there is startup code for this, the active learning class. And I'll give you Google that. It might come up pretty high anyway. But yeah, it's at that URL there. So GitHub, my account, active learning class. So that has the starter code for transfer learning and active learning, plus a set of I think about 200,000 sports-related images. And so this is something that you can get started on today with a number of active learning techniques that we spoke about, and also playing around with transfer learning, and even with access to that second to last layer of the net, so you can play around with things like clustering techniques there. So with that, I'd like to thank everyone for coming today, and I'll pass it back to Bill to open it up for questions.
Well, Robert, hey, thank you for that excellent presentation. We'll get started with today's Q&A session. I want to thank the audience for their participation. We had a lot of questions that have come in during this presentation, and we'll do our best to get through all of them in the time remaining. So during the QA session, I'll leave up this screen with contact information for Robert if you'd like to contact him following today's webinar. So let's get started. Robert, lots of information there at the end about confidence scores. how are those calculated, and how do they correlate with the probability of the image actually being correct?
Yeah, great question. So the probabilities that you saw there are the softmax output from the TensorFlow model. So taking the final layer score across all those categories, and then softmax are just converting that into a 0 to 100 range for the percent probabilities, or 0 to 1 more accurately. So that's one kind of score that you can use. You'll often see that referred to as model confidence, but it'll depend on the machine learning model to what extent confidence is accurate. So if you're using Bayesian modeling, it really is confidence. For especially some of the more complicated sequence-to-sequence models, you'll see a preference for people to call this a score rather than confidence, score just being a more generic name. And then there's certainly a lot of other methods that you can use. So depending on your algorithm, it might have different metrics in terms of distance from the hyperplane, goodness of fit in your model, predictive change in the fit of your model. Really, any of these scores that are available to you in the machine learning algorithm that you're working with are something that you can look at in terms of being that numerical value, which will drive what you sample for. And in all cases, they should highly correlate with your actual accuracy of the model. And that's something that anyone can easily investigate looking at the precision and recall trade-off.
Oh, Robert, thank you for that clarification. The audience had just a little confusion over the definition of active learning. So let me just try and understand this. Does active learning always mean human labeling data, or are there any other definitions that could be included in the field of active learning?
Yes, active learning is specifically the part of machine learning algorithm where you're selecting the data for human labeling. So strictly, yes, active learning does always mean human labeling, and the process of making that as efficient as possible. But certainly, there's a lot of really closely related techniques. So the one I showed today here was transfer learning, where you're not requiring additional human labels, you're adapting other models. And you also see people refer to semi-supervised learning, where you take high confidence outputs from your model and assume that label is correct, and put that back into your model as if it was a labeled item. Those kind of approaches, the semi-supervised approaches, they're really hard to deploy at scale without introducing a bias, because obviously what your model is most confident in is things that it already knows well. And so, yeah, to the extent that you're able to introduce just a little bit more of human guidance, I recommend trying to do that rather than trying to play around with computer-generated labels.
Oh, terrific. Thank you for that answer. Now, the uses of active learning, do most of your clients come to you to improve the performance of existing ML models once they've made a start at it, or are a lot of folks coming to you to label data before they even get started because they don't have any labeled data to begin with?
We see a lot of both. We work with a lot of customers for their entire journey, from raw data to firstly just labeling raw data for them so they can get started with active learning. And we also see a lot of customers coming to us with existing models where they want to scale the number of labels they have, and also think about smarter ways to select those. I'd say that the latter is more common, that people have already built some kind of models, maybe it's a proof of concept, and they're coming to us at the time at which they're looking to scale that. But certainly we work in other situations.
Oh, well, thank you for that clarification. And in the event that I have an existing model and I want to improve it, what's the guideline for the right percentage subset to submit for initial evaluation? Is it 5%, 10%? Is there a formula or an algorithm that I can use to calculate that?
Yeah, it'll depend on your use case. So generally what I recommend is you think about the number of labels that you want for your least frequent class. So in this case, I think it was in the order of about 20 different sports. And let's say I know that the least frequent one is basketball. So I want to think about to what extent do I need to keep resampling for active learning until I get to, let's say, 10,000 labels. And so rule of thumb for an image labeling task like this, you'll start to get interesting results with 1,000 labels for a class. And you'll start to get usable results around 10,000. And so working backwards from knowing the minimum amount of labels you need for your least frequent class, that should help you understand what to sample. The second part of the response to that will depend then on how many cycles of active learning you want. So the more iterations you can do by continually updating your model, the better. Right down to one single image at a time in this use case, and that'll depend greatly on your pipeline. So the time it takes to get someone settled to review just one item and to retrain your model will really depend on how ready your model is to update and the people you're working with are to annotate.
Okay.
So certainly I would bias towards as many iterations as possible with active learning. But in practical terms, if it's only a few cycles, that can be fine too.
Right. Well, thank you. Thanks for that clarification. It's obvious that there is a role here for unstructured text and image data. Audience asks, is there a role for CrowdFlower in structured data?
Yeah, absolutely. So in the examples here, they'll just plain images, but we'll often see structured or semi-structured data where people want to apply additional labels to them. So you can imagine that rather than just being unstructured images, we already had a lot of information around them, like the time and date that they were taken, captions on those images, which probably had a lot of information about what sport they were already. And this is something that we see often. So people are coming to us with data that's already semi-structured or some information associated with it. And then it's really just up to our customer preference as to whether that information counts as context that the contributors can use when creating the labels, or if it's something that our customers just hold out and might include later in their models.
Okay, and just finally, does CrowdFlower offer really specialized workers? For example, if I wanted to submit X-rays to be reviewed by radiologists or pictures of skin lesions to be reviewed by dermatologists, is that a service that you offer?
We do, yeah. We work in specialized domains, including medical, finance, and a number of others. In fact, our lead computer vision scientist, when he got his postdoc at Harvard Medical School, he was the first person to show that crowdsourced workers could be as accurate as so-called medical labeling experts for looking at medical labels. And so these are always use cases that we're really happy to look at and give advice as to what extent you can engage the specialist contributors who work in our platform, or whether some or all of that task can be designed in a way that people without specialized training can solve it.
Well, Robert, thank you. Hey, by the way, what was that Quartz Port that was in that slide? Do you know?
You know what? I actually forget right now. I'm blanking on the name of it. Cornwall or something? I believe it's played only in Holland. The last time I gave this talk, I thought it was netball, and someone corrected me. So I'm hoping that the AI can take care of this for me, because clearly I'm not able to retain that information.
Well, Robert, thanks. Great answers. Some very good questions. And for those of you that asked questions today that weren't answered, we'll be sending all the unanswered questions to Robert and the CrowdFlower team so they can follow up with you after today's webinar. I have just a few quick announcements. If you'd please mark your calendars for March 20th and our next Data Science Central webinar, which will be the Analytics Lifecycle Revolution, Evolution or Extinction, to be presented by Alteryx. Also, I remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to CrowdFlower for their sponsorship, as well as to our speaker today, Robert Monroe, for his insight into today's topic. This is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on March 20th. Have a great day.